Hi there, everyone. We are Team Lyseia, and we are so incredibly excited to share with you the results of our work over the past couple of years now. Kind of a funny story as to how we all got together. It was the very first day of our biochemistry class, and our professor went to the front of the room and he said, "If you're interested in entrepreneurship in biotechnology, send me an email." And of course, who could turn that down? So all of us ended up sending him an email, and we ended up joining what is now known as the ChemH Entrepreneurship Club. And without having known each other before, I think we kind of got lucky to have been placed on the same team together. Not only do our personalities fit quite well, but we also have a diverse array of academic backgrounds that we come from. So I'm Zach Rosenthal. I'll be graduating from Stanford tomorrow with a degree in chemistry.
I'm Christian. I'll also be graduating tomorrow with a degree in chemical engineering and electrical engineering.
And I'm Maria. I graduated a year ago with a degree in bioengineering, and I'm currently pursuing an MD PhD at Stanford.
So we've been working on this project for almost 2 years now at Stanford, and we're really excited to kind of update everyone as to how far we've come. The problem of antibiotic resistance and of multi-drug resistant organisms in particular is already an issue. In 2013, there were 2 million illnesses, along with the corresponding 23,000 deaths. But what's even more astonishing is how this problem is expected to exponentially become a bigger deal. By 2050, there's expected to be a global economic cost of $100 trillion, along with 10 million deaths per year. In fact, the number of individuals that will die from multi-drug antibiotic-resistant organisms is expected to be larger than the number of individuals who die from cancer. And what's even more astonishing is no major pharmaceutical company seems to be viewing this as an issue worth concern, with only 7 drugs currently in any advanced form of clinical trial. The problem has become so large that the director of the CDC has described this as a nightmare scenario. And so now we will tell you what our proposed solution is.
Our solution is to use engineered bacteriophage endolysins. Endolysins, or lysins, are proteins used by bacteriophages to break out of bacteria. We have identified several lysins with broad activity, and we have engineered them to improve their efficacy against gram-negative multi-drug-resistant bacteria. Compared to traditional small molecule antibiotics, lysins show more promise because resistance development is very little to none. The way our protein works is that it first penetrates the outer membrane of the gram-negative bacteria, and then it breaks down the peptidoglycan layer, and due to the high internal osmotic pressure of the bacteria, leads to cell lysis and cell death. After pitching our idea at Stanford, we got seed funding from Stanford ChemH, an institute within Stanford, to do a set of pilot experiments. With the money, we were able to express and purify our protein for testing. As you can see, in this plate, we did not add any antibiotic, and in this middle plate, we added our protein. And on the right, we added kanamycin, a known antibiotic. From these results, you can see that our protein has the same capacity as kanamycin to kill our gram-negative model E. coli. And with these positive results, we're going to scale up our production of protein and send them to a contracted research organization to test against the pathogens that we're really interested in. Along this way, we never really expected to go from slides to actual experiments, and we learned a lot of valuable insights that Maria will explain.
Thanks. So the first takeaway that I want to share with you all is that it's okay to buck the status quo. So in the pharmaceutical industry, when you're looking at developing drugs, a lot of people think that if you are just an undergrad, you don't have much to contribute. Or, I mean, you guys are just high school students, and look what you've already contributed. So don't be afraid to go out there and say, you know what, I have a skill set and I can do this, even though people think that I might need a PhD or an advanced degree. Because there's so many issues in the pharmaceutical space that need to be addressed. And anyone at a basic research institute who has access to a wet lab can make huge strides. So don't forget that you have the power to do that.
Don't be afraid to be naive. None of us knew anything at all about multi-drug resistant bacterial organisms before joining this club. It's even a mouthful to say. But I think that maybe one of our biggest strengths when first approaching this problem was the fact that we were naive. We were able to broadly look at all of the available options that were currently being pursued around the country And without any preconceived notions as to what would be a good or bad idea, we were able to come to our own conclusions, combine different approaches, and ultimately settle upon our proposed therapeutic.
You should also reach out and reach up. When we first started the project, we reached out to a lot of industry experts and professors, both within Stanford and outside. And sometimes it was daunting because we felt like they wouldn't be interested in talking to us about our idea and seeing what they thought of. But in fact, many of them have reached out back and have gave us invaluable insights on the way they think our product should have gone and the way they think that our product is.
Related to that is that you want to get as much advice as possible, but at the end of the day, you and your team have to make your own decisions. So when we were working on this project, we met with a bunch of professors, physicians, people in local biopharma companies, and a lot of them were encouraging and gave us advice. And some of them said, this will never work, stop wasting your time, don't do this. And people might say things like that to you. Some of your projects might seem impossible, right? But we're engineers and we make the impossible possible. So don't let a few naysayers get you down. Take all their advice, maybe they have good criticisms, and find a way to address them, but still stay true to what you and your team want to do. So this point is really important to me. I think sometimes in our society there's this false dichotomy where you can either start a company or pursue higher education. So you could drop out and have a startup. A lot of my friends at Stanford, for example, dropped out and did startups. And I think that you can do that if you want to, but we all have seen the value of continuing into higher education. So Zach's going on to get an MD, Christian's getting a PhD. I couldn't decide, so I'm getting both. And you can do that and still have a company and still make a difference. So don't think that you can either be an entrepreneur or go on to be a scientist or a doctor. You can do both. And I think, we all think, that you could actually be a better inventor by getting more education. So you don't have to say no to your educational goals to pursue your research and your entrepreneurship goals. And the last point I want to make is share your work. So you might think that your projects are early stage, you're not done yet, you don't want to show it off to the world because they might notice that it's an unfinished prototype. I wouldn't worry too much about that. We shared our work really early, and because of an article that was published in just an on-campus publication, an NPR correspondent had come to Stanford and needed to cover a science story, and he saw that article and he's like, oh, okay, I'll come talk to these young inventors. And that ended up getting us a lot of new press, new funding opportunities. So don't be afraid to put yourself out there. Usually press can only be helpful, and it can not only get you more funding and more opportunities, but it can inspire other people your age to pursue inventions. Because when I was in high school, I had no idea that I could do the stuff that you guys were doing today. So even by showing other people that they can do that, you're doing what you can to push other students forward. So share your work. We wouldn't be standing here today without the help of the people who really made this possible from the beginning. So at Stanford, we were lucky enough to be mentored by a chemical engineering professor, Chetan Khosla, who's had our back from the beginning and helped us with the initial funding. We also had industry mentors, so from both biotech and investment banking, who have had our backs and showed us how things work in the quote-unquote real world outside of the university. And lastly, we do all of our research at the Macromolecular Structural Knowledge Center, which is like a lab space on campus. And so Mark and Daniel are there, boots on the ground every day, helping us to express and test our proteins. And lastly, of course, I'd love to thank the Lemelson-MIT Foundation for bringing us here, for the funding, and perhaps most importantly, for letting us interact with you guys, because you are going to be standing here one day, and I can't wait to see that. Thank you.
We have about a minute and a half if anyone has a question for the team. Oh, way up in the back.
The possibility that these bacteria could evolve to resist the protein you created, and how do you propose handling that?
Sure. So people have done experiments with lysins, and the reason we think they're so good at not developing resistance is that you can culture bacteria for a bunch of generations and see if they develop resistance. And with standard antibiotics, you typically develop resistance very readily, but when people have tested other lysins, you don't see development in 50 generations. So we're hoping that our technology will work in a similar manner.
Are there any other questions?
Yeah, so what's patentable about your invention, and who's going to own it?
Yeah, so we hope to own it initially. We want to incorporate and use our startup to get it through some of the initial stages. And what's patentable is that we're using protein engineering techniques that are somewhat novel, as well as starting from starting material that's novel. So we'll probably go after a composition of matter patent over the final form of the protein that we're going forward with.
Thank you, guys. We're going to move on to Apoorva.